Is Melanie. And we're recording. Awesome. I am one of the coordinators for this event. And welcome to Science in the News. So before we get started, I just want to give a little quick introduction about each of our speakers tonight. So first up, we'll hear from Brahmi. She's a member of the chemistry department at Yale, and her research involves mapping interactions of splicing proteins and RNAs. And an exciting fun fact about Brahmi is that she just became a US citizen last June. Next, we'll hear from Jessica, who's also a member of the chemistry department at Yale, and her research is on machine learning for environmental chemistry. And a fun fact about Jessica is that she loves to sing sea shanties while fly fishing the surf. And finally, we will hear from Sri. He's a member of Mechanical Engineering and Material Science Department at Yale, and he studies soft robotics and mechanical metamaterials. And in addition to that, he is also a certified yoga and meditation facilitator. So before we get started with our first talk, I'd like to introduce some of the common themes that will come up throughout each of the talks. The title of our set of talks is Modern Problems, Modern Solutions, An Outlook into the Future. So in each of the three talks, our speakers will tell us about some significant problems of our modern era, as well as solutions that are enabled by modern technology. And so some of the central themes that we're going to see coming up again and again in these talks is the interaction between nature and technology and how they really impact one another, and how we can be inspired by nature to create technologies that will help improve our world. So in the first talk, we will start from the top, the Earth's atmosphere. So we will hear about a serious problem that our planet recently faced and how people around the world stepped up, got together, and created a really amazingly successful solution. After that, we will go down to our oceans, coastlines, lakes, and rivers. We will learn about how some really successful solutions to global food shortages have created new problems for aquatic environments. And we'll hear about what's currently being done to address these problems. And then finally, we'll dive under the surface here and learn about robotic turtles. So robotic turtles, along with many other types of robots that are inspired by nature. And we will hear how these nature-inspired robots may someday soon help change our natural world for the better. So once again, I will introduce our three speakers. And with that, I will hand it over to Brahmi to start with her talk.
Thank you, Melanie, for that lovely introduction. I am going to share my screen now. Okay. So today I will be talking about the atmosphere's desperate cry for help, at least back in the 1970s, and the major international solutions that address the problem and where we are today. So, as we all know, global warming is the most urgent environmental crisis, and it is something that environmental chemists are very concerned about, and we know the side effects of global warming. We know that it has resulted in the rise of food insecurity, melting of the glaciers, and a lot more. And we should be concerned. But this wasn't the priority and the top concern back in the 1950s to 1980s. It was something else. And that is known as the ozone hole. And that is the topic of my conversation today. The ozone hole is basically a region where we have very low amounts of ozone. And I will go into detail in the following slides, but this center right here in purple shows the very low amounts of ozone. At least 60% of it is gone. And so now I will go in detail into what the ozone levels mean, what ozone is, and what it does in terms of the environment. So ozone, which makes up the ozone layer, is the Earth's natural sunscreen. The ozone layer itself is the Earth's natural sunscreen. It is protecting the Earth from harmful UV rays. So this graph figure shows the amount of ozone concentration as we increase in altitude increases, and it reaches its max in the stratosphere. And about 80% of it is in the stratosphere itself. And to give you a little bit of context, we have airplanes that usually fly in the tropospheric region of the atmosphere, about 0 to 10 kilometers above the Earth's surface. And we have weather balloons that are usually located in the Earth's stratosphere. And this is the basics of what the ozone layer does. We have a nice thick layer of ozone made up of ozone molecules, and that is essentially covering the Earth's surface, and it's protecting it. Now we have harmful UV rays given off by the sun, and it's essentially being absorbed by the ozone layer, by the protective layer, and gets deflected. You can think of it that way. And on the right here, I have a molecule of what ozone looks like. It is 3 oxygen atoms together. But the problem that we saw in the 1950s and 1970s was that this ozone layer was shrinking. And what that means is that the less ozone layer results in less protection from these harmful UV rays, which is very concerning because we already started seeing those effects of what that can do. The destruction of the ozone layer resulted in more UV rays, and that resulted in not only the ozone layer breaking down, but we also faced unhealthy consequences as a result of that. So where does that lead us to today? It is still relevant because we still see these ozone holes in the world, across the world. And particularly we have regions such as the Antarctica and Australia. And we also have regions in the Arctic that are facing very, very low amounts of ozone during some times of the year. And what this means, we already know in Australia has the highest rate of skin cancer in the world today. And it does certainly have a direct relationship with the fact that Australia has an ozone hole and it's not being protected by those harmful UV rays, which is why it's also very important to wear sunscreen all the time because it's protecting us from some of those UV rays that are entering the Earth. The ozone layer is very good at what it does. About 98% of harmful UV rays are being absorbed by these ozone molecules, but because that ozone layer is getting smaller and smaller and smaller, we're starting to face these consequences. So what are these consequences? Well, we know that skin cancer is the largest effect that we've seen so far. It has destruction of the ozone layer, means more UV rays entering, and UV rays have resulted in about 90% of skin melanoma. We also know that damage done to the eye can result in cataracts being formed because those UV rays are hitting the retina. So on the left, we have a normal eye, but on the right side, we have a damaged eye. Again, that's where the UV kicks in. We also have damage done to the environment around us. We have crops being destroyed. We have an effect on the agriculture, and we also have damage done to the marine ecosystem. And all of these, because they're tied to one another, we'll see that they are also resulting in effects done to us indirectly because of food insecurity, for example. So now that I told you what the ozone hole is and what the ozone layer does, I would like to share what the cause of the ozone destruction is. Why are we seeing that phenomenon? What is going on with the shortening and the depletion of that ozone layer? Well, in 1974, these 3 wonderful chemists came together and they discovered in the science community that, okay, there's definitely a link between these chemicals and the depletion of the ozone layer. And these chemicals were identified to be CFCs. So these CFC molecules are known as chlorofluorocarbons, and they're particularly potent because of the chlorine atom, which is indicated by these blue regions right here. Now, I can show you a quick mechanism of what happens in the atmosphere. When we release these chemicals, known as CFCs, there are major consequences and mechanisms happening in the atmosphere. But first, I would like to talk to you about where these CFCs are found. We know that CFCs were found and used very commonly back in the day in propellants, aerosols. We have foaming agents that use them. We know that the coolants in refrigerants, automobiles, air conditioners, all of them used CFCs, including fire extinguishers that used halogen-based chemicals, also very toxic to the atmosphere and the ozone layer itself. Okay, so we have all these products being used in the late 1900s, and we know that these are causing massive, massive amounts of depletion of the ozone layer. Well, what's the science behind it? We're releasing all these chemicals in the air. We don't know what's going on. Again, those three scientists, they won the Nobel Prize in 1985 for the discovery behind the science of the ozone depletion. So what exactly is going on up there? When the UV, so we have chemicals being emitted, they reach the Earth's atmosphere, and UV rays hit these molecules known as CFCs. So once that happens, we have the molecule gets separated, the chlorine atom gets separated from that molecule, and that results in chlorine going around out and about in the atmosphere, and then it finds the ozone molecule that's essentially making up the ozone layer. And what it does is it strips that ozone layer of its oxygen atom. And now we have ClO and we have oxygen, so hypochlorite and an oxygen molecule. But now we notice that there is a destruction of, we have one less ozone molecule, which is not good. And then we have another oxygen atom that's floating in the air, and then it comes about and sees that hypochlorite atom molecule. And what it does is that it strikes again, and now it releases that chlorine atom. What this means is that we're able to start the cycle again. And now the process repeats. That same chlorine atom can go on to destroy about 100,000 ozone molecules, which is particularly concerning. And then with CFC, with the continued use of CFCs, we can actually see that Earth would lose all of its protection. So the ozone layer would practically be gone. And CFCs, what's so interesting about these molecules and chemicals is the fact that they can stay in the atmosphere for a very long time. So we know that they actually can stay stable up there for about hundreds of years before they get kicked out. And so they can keep reacting. This is just a quick representation of what the Earth would be like by 2060s if we continue to use those chemicals in refrigerants and sprays and propellants and all of that stuff. And we know that this scale down here shows that as we go to the blue regions, that means less ozone is present. And if less ozone is present, then we have less protection from those harmful UV rays. And so we know that by 2060, essentially, the Earth would practically be inhabitable, which is really bad. And this was all discovered, in the last 40 to 50 years. We know that this was concerning and something needed to be done ASAP. So what was implemented was known as the Montreal Protocol. In 1987, almost all countries around the world came together to ratify this international agreement, and they all decided that we would use this amendment to ban the use of CFCs. And this was actually implemented and taken into effect in 1991, which is relatively recent if we think about it, but we won't start to see the effect until much later on, because like I said, CFCs, like those chlorine atoms and CFCs, they like to stay in the atmosphere for years and years. So it'll take us a while to start seeing the effects of that. But we do expect to see the ozone layer coming back to its original levels by the 2060s. At least that's what scientists are saying today. So the Montreal Protocol, it reduces the CFC emissions and practically banning all use of CFCs. We know that, again, these were very dangerous to the ozone layer itself, and they were being used up until the 1987, up until the Montreal Protocol, and a really high rise in millions of tons of these CFCs being put out there into the atmosphere. But after the Montreal Protocol of 1987, we see a rapid decline in the use of CFCs, which is great for the atmosphere and great for the ozone layer. And this is a quick representation of what the world would look like today, and not just today, but like later on as well, up until 2060s, with Montreal Protocol on the left and without Montreal Protocol on the right. And the more blue regions you see, the less ozone there is. So on the right side, we see that eventually in the next 3 to 4 decades, we would have zero ozone present. And that is very dangerous, and we probably wouldn't be here by that time. So the Montreal Protocol was extremely, extremely effective, and CFCs were abolished. But we still use refrigerants, we still use coolants and fire extinguishers and aerosols and propellants and all that stuff. So something had to be replaced. Something needed to take the spot of CFC chemicals. And what that was is something known as hydrofluorocarbons, HFCs. Now, these are great because they're not ozone depleting. They don't contain chlorine atoms that are depleting the ozone. But they're also posing another threat, and that is they are one of the molecules that are harming in terms of global warming. They have a really high global warming potential, very, very potent in terms of warming of the earth. And that is particularly concerning because, like I said, that is our #1 climate crisis as of today. And if we were to compare CFCs with carbon dioxide, for example, the global warming potential of carbon dioxide is 1, but the CFC global warming potential is over 12,000, which is insane. So with global warming on the rise, 2019, again, we know that it was one of the hottest years. We are facing severe consequences. We have food insecurity worry about, species dying, and we have starvation and damage done to the marine ecosystem and a lot more. So I just wanted to leave you off with that. However, there is a bright side to this. We know that there is something known as the Kigali Amendment implemented back in 2019, and that is to essentially significantly reduce the levels of these HFC molecules, and they're trying to find alternatives that would A, not be ozone depleting, and B, not contribute to the global warming of the earth. Now I want to hand you guys over to Jessica Fries. She's going to be giving you a wonderful presentation about eutrophication. Thank you so much.
Thanks, Brahmi. So Brahmi has just told you guys how the ozone hole has hurt our food security through the destruction of plants, as well as hurting many other things. While the fixing of the ozone hole has made it so that plants are experiencing less UV damage, producing enough food for a growing population has in fact always been a concern. one of the many remedies that we have applied to address food insecurity has been the modern creation of mass fertilizer production. However, this solution has created another problem that actually threatens our food, water, and economic security. And that is the problem that I would like to discuss with you today. The problem of excess nutrients, especially from fertilizers, polluting our watersheds. The abundance of fertilizer has led to much of it being washed off by rain into our watersheds as something known as runoff. And this creates global devastating effects, as you can see in these pictures. Now, while these pictures may look colorful, and in fact, the largest one is in fact kind of beautiful, they actually depict the overgrowth of algae in a process known as eutrophication. So let's start by explaining the two main problems that result from eutrophication: the creation of dead zones and the production of toxic algae. I will then follow up by talking about the impacts of this problem and finish off with some solutions to eutrophication. So beginning with the creation of dead zones. The creation of dead zones by eutrophication starts when excess ammonia from fertilizer is washed as runoff into a body of water. Once in the water, bacteria transform ammonia into the chemical nitrate, which is shown up here at the top. Nitrate is an algae food, and this excess nitrate leads to an algal bloom. This algal bloom will block sunlight from the plants below, killing them. When nitrate is all used up, the algae are also going to die and get degraded by aerobic bacteria. Aerobic bacteria sap oxygen from the water as they eat the algae. And because there is now no longer oxygen in the water and there are no plants left to resupply that oxygen, any fish or aquatic life that is unable to escape from that area will die. And that is what creates dead zones. And that's what this picture is showing. This is a depiction of a huge algal bloom that, if not dealt with, will lead to a dead zone. But before we advance into the impacts of that, let's talk first about how toxic red tide algae are formed. So this eutrophication process again begins with excess nutrient runoff flowing into our watersheds and producing nitrate algal food. This food produces a bloom of algae, but this time it's something known as red tide, which produces a toxin known as domoic acid. The acid will concentrate in the skin and shells of aquatic species and the air around affected water. But the problem of dead zones and these toxic algae actually occur across the entire globe. So let me show you that in this picture here. So as we get into impacts, you see that all of these red dots are showing coastal dead zones that exist. And the blue swaths are showing open ocean dead zones. Clearly, many of these dead zones are quite big and impacting huge amounts of our globe. So let's take a look at the more specific impacts. Before we even reach the algal blooms that cause dead zones, that cause the toxins, ammonia is turned into that algae food known as nitrate. And when this nitrate is created in high concentrations, it's actually able to surpass our water treatment processes and make it into our homes. And while nitrate is not good for any human to consume, especially for babies, nitrates can lead to low oxygen concentration in the blood and lead to impaired function and what is known as blue baby syndrome. This in animals and other smaller creatures leads to increased stillbirths and reduced vitality. And the toxicity and low oxygen concentrations produced from eutrophication also lead to massive aquatic species die-off, which cause horrible stenches and fill the water with dead animals, which have to oftentimes be cleaned up with large nets to prevent the poisoning of your local waters. So let's move on to food security. Dead zones, looking specifically at dead zones, in their most passive sense, are going to decrease habitat for aquatic life. But at worst, they're going to kill entire food-producing ecosystems. And this is occurring not just in oceans, as I showed you with that coastal map, but also in inland waters as well. But even more concerning than dead zones to our food security are the domoic acid poisonings, which can echo up a food chain. For these smaller creatures, seals, ducks, other aquatic birds, this domoic acid poisoning will oftentimes kill those species. But for humans, it's not much better. A poisoning amount for a human is 0.075 parts per million per day. And the results of being poisoned in this way can lead to paralytic and amnesic shellfish poisoning, which causes severe nausea, dizziness, burning in the brain, loss of large motor control, and even death, especially in elderly populations. However, if 0.075 parts per million sounds small, it's important to know that in single clams for the past couple years, 200 parts per million have been found across the Pacific coast of the United States. To try to mitigate the consumptions of these clearly dangerous amounts of domoic acid, state and federal governments have actually had to perform daily tests on aquatic species to determine the safety. You can actually see along Connecticut's coasts the warning signs about whether or not the shellfishing is currently safe. However, obviously, if we have to constantly be checking for this, this is going to severely limit the non-commercial harvest of shellfish due to such dangers. And with all this discussion about the impacts to food, it should be clear that those who rely on the fish market for income or tourism will also suffer greatly from these toxic blooms and dead zones. As just an example of the impact, commercial and recreational crabbing was prohibited off the coast of Washington state throughout much of the 2015 through 2020 seasons due to the domoic acid levels being too high. We sit here thinking that COVID shutdowns have been bad. Imagine being shut down for 5 years. But it expands beyond anecdotes. According to NOAA, the seafood industry of the United States is comprised of 1.25 million jobs and produces $1.7 trillion in sales in 2017 alone. So clearly that's a large sector for a nation. But there's also a recreational market of 500,000 jobs and $750 billion a year that relies on this. And furthermore, if you're getting skin irritation, burning of the eyes, and coughing just from being around a beach that has red tide, you're not going to be interested in the hospitality industry that currently makes up $900 billion a year. But if the size of abstract markets across the country still doesn't hit close enough home for you, let me tell you a brief story about the Housatonic River in Connecticut. So from the 1930s to the 1970s, General Electric in Massachusetts dumped excess PCBs into the Housatonic River. Now, PCBs are not the same thing as eutrophication, but it's a good example of how the loss of an aquatic recreation area can kill an economy in town. An EPA study that was conducted in 1996 to determine the extent of the damages done to the recreation and fishing found a conservative estimate of $250 million of damages. Estimating the damages to the surrounding economy was deemed undeterminable at that time. But speaking in anecdotal discussions to people who lived in that area of the northwestern part of Connecticut and worked around that economy, many of the businesses surrounding the Housatonic River had to shut down. And the people that I spoke to also had to leave that area due to the failing economy. Now, if you go to the northwestern Housatonic River area, there's little more than a gas station, a general store, and a single fishing shop in New Canaan. And Connecticut and Massachusetts are still cleaning up the river and advise citizens against consuming any animal from, in, or around the river. This type of thing can happen everywhere, and it is. It's a problem that is here and it needs solving. So what are some solutions? The two main categories of solutions to address eutrophication are mechanical and chemical. Mechanical solutions will involve the collection of algae after they have formed or the filtering of nutrients before they reach the watershed. Chemical solutions involve application of a chemical to polluted water to extract or transform excess nutrients or toxins. The most common mechanical solution is what's known as a riparian buffer. And riparian buffers are formed along bodies of water, and they are dense areas of grasses, bushes, and trees. And as excess nutrients flow as runoff from fields or from rain from fertilizing new grasses, they will actually get soaked up by these plants that are densely placed along a water body. This is actually a picture showing a real riparian buffer that was built along the Norwalk River 2 years ago. And the Norwalk River has actually seen much less algal growth since the planting of this buffer. Another mechanical solution is the scrubbing of algae covering lakes. And this generally involves the trailing of nets to plow across a river and pull in algae that has covered the surface before it can die and lead to those low oxygen dead zone sections. This is especially important for lakes because they have low flow and they trap the animals, the fish in them from moving to more oxygenated waters. And then a final mechanical solution to look at is the multi-step water treatment processes that are performed going into our home use. The multi-step process includes mechanical separation of solids from liquids and a combination of mechanical and chemical filtration. So mechanical methods have both pros and cons. Many of these methods are passive, such as the riparian buffer that you can see here in the background. Once it's planted, you don't have to do too much. They also create prettier landscapes. A lot of these buffers include a lot of flowers that attract bees and butterflies and birds. And there are a few dangers to planting some extra bushes, but they can be slow to implement. This buffer did in fact take 1 to 2 years to grow. And they're less effective in high nutrient concentration situations where you have lots of nitrate that could still get past either the buffer or the filtration system. Also, mechanical collection, when you look at nets going across the river, can kill a lot of fish, which is kind of against the point of what you're trying to do. And if you make these riparian buffers, you have to make sure that you still build paths into them. Otherwise, you're impeding stream access or people have to walk through brambles and no one wants to do that. Chemical solutions, on the other hand, oftentimes involve catalysts. And catalysts are molecules that alter chemical reaction pathways, or you can think of them as making chemicals do their jobs better. This specific catalyst that I'm showing right here converts ammonia to nitrogen gas. To give you an example of how catalysts can be used to change the reaction pathway, let's look first at the nitrogen cycle as it happens in nature. So we'll start at the primary plant food, ammonia. This gets converted by the nitrogen cycle into nitrate, which is a primary algae food. That is then quickly converted into a toxic species, which is quickly converted into harmless nitrogen gas. The nitrogen gas gets turned back into human food and other nitrogen products, which then turns back into ammonia and the cycle continues. Now, obviously, from a chemical perspective, we want to make sure that we are also not having a buildup of this toxic species, which in nature, once it's created, gets converted extremely quickly to harmless nitrogen gas, which makes up most of our atmosphere. So we want to make sure that any catalyst that we create will avoid this. We also would like to prevent the creation of this algae food, nitrate. So what we can do in chemistry is create a catalyst that will insert into those steps and take us straight from ammonia to nitrogen gas, removing nitrate, which is the algae food, and removing the toxic species that we don't want to touch at all. We can also tailor these chemicals so that they are in fact faster than the natural processes. And that will help us in addressing these problems if there's a big spill. So chemical solutions, whether they're the catalyst I showed you or something else, do also have pros and cons. They have super quick application. You can take the chemical and apply it right where you need it immediately. You don't have to grow anything. They're also space efficient. You don't have to have 2 to 10 feet of riparian buffer in a spot. You can just apply the chemical to where you need it. You can apply a certain amount to match the amount of problem that you have. So if you only have a little bit of runoff every year and you know you're only going to have a little bit of runoff, maybe you only need a little bit of chemical. But they take time to develop and perfect. If we want to improve upon nature, then we have to take some time to do that. It's also harder to be sure that you're going to have a minimal negative interaction with the environment. As many tests as you do in a lab, there are always things that are new and different in each different environment you may want to put this in that you may not know about. And because of that, if you have excess or non-targeted use, you're going to have an increase in the unintended consequences. And so because of that, you must apply chemicals in an extractable way. To give you just an example of how we use chemicals in real life, if you think about the BP oil spill, which is pictured here, chemical dispersants were applied by a plane over the oil spill in order to allow the oil not to group up and instead spread out and become less toxic to the environment. So when it comes to choosing which solution to apply, one must first consider what the problem is. If your problem is algae already being present on a lake or a river, then a mechanical solution to remove it is necessary. If there's a huge spill of fertilizer or ammonia, then application of a chemical is likely the best remediation. If prevention is the plan, riparian buffers provide a long-term passive benefit, while additional chemical filtration at points of high confluence or industrial sites offer good options as well. And as I've already mentioned, a mixture of chemical and mechanical methods are already employed in water disinfection systems for home use. So where does that leave us? Well, eutrophication is a process that comes from excess nutrient runoff, and it's causing global devastation in the form of dead zones and toxic algal blooms. This is affecting our water, food, and economic security. But we're looking towards mechanical and chemical solutions to employ and develop to help with these issues. What's most important right now is that we need much more awareness of the eutrophication problem because it's happening everywhere. And in fact, it's in our hands, it's also in your hands. You can find out more and make yourself more aware of these issues by going to NOAA or the Connecticut Deep websites. Both of those have fantastic resources on this problem and how they're seeking to address it. And if you want to get involved on the ground with building riparian buffers and looking at other solutions, Save the Sound and Trout Unlimited are doing that. So with that, I'm going to pass it over to Sri, who is going to tell us another way in which nature is inspiring us.
Thank you, Jessica. Thank you, everyone, for joining. So far, we have heard two wonderful talks on different environmental problems and their potential solutions. So here, I'm going to slightly switch gears and talk about robots. So robots that are inspired from nature. So my talk is on soft robotics, which is a bio-inspired paradigm, which could potentially act as a solution to conserve our environment as well. Robots. Robots are machines that can perform a given task millions of times with same accuracy and precision. Here is an example of industrial robots in a BMW manufacturing plant assembling a car. You can see how elegant they are and how precise and accurate they are, and they can do this same process millions of times tirelessly. But if we take these robots, which are in a programmed and structured environments like industry floors, and put them into real world and ask them to do simple tasks, they fail miserably. Even to walk or to open a door, even a simple error in the measurement or uncertainty can have catastrophic results. So this has to do with the problem of rigidity. So rigid structures can be precise and accurate, but they cannot adapt in an unstructured environment with many uncertainties around. Even more so, in this modern era where robots, the proximity between robots and humans is decreasing day by day, we don't want such rigid, hard robots to be around us or our kids. So engineers have always been taught to build things that are strong. What I mean by strength is a strength of a material is defined as its ability to withstand failure. So how much load it can take before it breaks. And we have always been taught that rigidity alone can give you strength. But strength doesn't always imply rigidity. which is very obvious if we see natural systems. For example, here is a shark, which is considered very strong, being overpowered by an octopus, which has tentacles that are very soft. So nature shows that we can create systems that can be soft yet strong. There's a famous quote by Professor Stephen Vogel from University of California, where he says that nature actually prefers soft materials. So it uses soft materials frequently and stiff materials sparingly. Even in our own human body, 80% is made of soft materials. So traditional robots, as I've shown, are made up of these rigid links with joints to move across. But unlike these, soft robotics is a field where these robots are made of soft, flexible materials. So as you can see here, they are this continuous systems like elephant trunks or octopus tentacles. So because of this, the fabrication or the design is not intuitive for us. So we fabricate them using a fabrication technique called molding and casting, as you can see in this video. So we have a mold and we are pouring this soft rubbery material and we remove it from the mold. And as we actuate it pneumatically, so they are pneumatically powered, that is, we pump compressed air and it bends. So that's a simple soft robot. So what can we do with such robots? So here is another example of a completely soft untethered robot made at Harvard. So this can move in snow, walk across fire, and it is very strong. So as I mentioned, strength of a material is its ability to withstand failure, and it doesn't fail even a car moves over it, and still it goes unperturbed. And here is another example of a soft robot, which is a pipe climbing soft robot made of two different building blocks. One, as you can see, the orange blocks, which just hold the pipe, and the green, which just extends. So using this holding and extension, we have this inchworm gate robot that can crawl pipes, which is completely soft. So there are many aspects we can inspire from nature other than softness. And the other important aspect is intelligence. Nature is inherently intelligent. For example, see this octopus moving through an opening to capture its food on the other side. So the opening is significantly smaller than its own body size, but it uses its tentacles to observe the environment around. It thinks and plans on the go, and it changes its own body to move through the opening to capture food on the other side. So this specific kind of intelligence is called embodied intelligence. Before defining what this embodied intelligence is, let me give a functional definition of what intelligence is. So intelligence has many different definitions. So let me define a functional or an operational definition which we use in robotics field. And it has three components to it. The first is perception. So perception is the ability to observe and comprehend complex situations around us. So that's perception, which we all have. Second is control and action. So based on what we observe, making choices and decisions on the go and acting according to the decisions. That's the second component of intelligence. And the third one is learning. Continuously learning based on what we observed and the decisions we make, we change our decisions. So that's in a loop. So this three components combine what we call intelligence. And in robotics field, each of these components have systems corresponding to them. So for example, the perception is done by sensors. So sensors are systems that can perceive and comprehend complex situations. Examples of sensors is a simple camera, which is a vision-based sensor. And on the other hand, for control and action, we have components called controllers and actuator. So controllers are systems that can make choices and decide. And actuators are systems that adapt and act according to what choices we make. And finally, we have algorithms that learn and learn from experience continuously and autonomously from what we observe and what decisions we make. So these three components are basically what we call intelligence together. And as I mentioned, nature has this a different kind of intelligence, which emerges not just from the brain, but a strong coupling between body, brain, and environment. And this is called embodied intelligence, which we all have. So we can inspire this embodied intelligence and put it into robots. So here is an example. So here is an example of a robotic fabric. So generally we have fabrics all around us, but can we make fabrics, design robotic fabrics that can behave, move autonomously? So here we sewed fabrics with smart fibers, and when you heat them, you can see that the fabric is standing on its own. So the intelligence is embedded into its own fabric. So that's an example of embodied intelligence. And on the other hand, we have another system where a robot can change its own shape to move across obstacles. So generally in robots, traditional robots, they avoid obstacles, but here this robot changes its own shape of its body so that it can just roll over the obstacle instead of avoiding it. So the intelligence is embedded into the body. So this is another example of embodied intelligence. So we have developed, and here at Yale, I was part of a project where we have developed this amphibious robotic turtle with embodied intelligence. So the problem or the goal of the project is to design an amphibious system that can move through this complex terrain of water and land. So it can swim and walk. And to design such a system, we have taken inspiration from two natural systems. The first one is this large turtles, which are Galapagos turtles that have cylindrical limbs that help them move on land. So that's one system. And the second is the sea turtles, which have very flat flipper-based limbs that help them swim efficiently in water. So we have taken inspiration from these two species and developed an intelligent limb. So the intelligence here is that this limb can change its shape from semicircular or circular to being flat, as you will see in here. So in its so it has two actuators which are pneumatically powered, that is, we send compressed air, then it changes its shape and becomes this semicircular limb, as you see here. And then once we deflate it and heat it, it goes back to being flat flipper based, which could help in swimming. So let's see if we put this on a robot. So here is an example where we took this and put it in a semicircular shape and asked it to walk, similar to the turtles which you saw previously. So you can see that it walks very similar to how a turtle walks. I don't know if it's lagging a bit, but I hope you can see that. And on the other hand, when it is in a flipper shape, we asked it if it could swim in water. And as you can see, it can swim in water, very similar to how sea turtles swim. So here we have developed a robotic system that walks like a turtle, swims like a turtle, but not an actual turtle. So where can we use this soft robots? So soft robots can be directly used in manufacturing, especially in handling soft systems like food objects, like vegetables or bakery items. So here the grippers or the fingers are made of soft systems so they can handle soft objects. So that's one direct application. And also because of their softness, they can work in hand with humans in the loop because they are soft and they have safe human robot interaction. So that's another example in manufacturing industries. Other than this, they could also be used in biomonitoring and ecological conservation. So here is a robot, Sophie, a soft robotic fish developed at MIT, which is very, very similar to a natural fish. And it does biomonitoring deep oceans without disrupting disrupting the ecological environment around it. So that's another example of an application. And also, they can be used as assistive technologies for elderly and for army and first responders to assist in their daily activities. So they could be just worn and they can assist people. So that's another application to improve the quality of life. So I hope I have convinced you that the future will be soft. And we took two main inspirations. The first thing is that we can design systems that are soft, flexible, yet strong. And also this concept of embodied intelligence, where the intelligence can be embodied into the body, not just in the brain. So to summarize all our talks, so generally when we always think that the technology is negatively impacting the nature around us, but we can design intelligent technologies that can positively impact and even improve the quality of life of people. And thank you so much for listening to our talk. And if you have any questions, we could take some questions at this point. Thank you.
That was really terrific. Thank you. All three of those talks were fascinating. I might have a nightmare about a soft robot, though. The way they move is a little bit too similar to something that's actually alive. So the one upside about being in a meeting format tonight is that I do welcome you to unmute and camera on if you have any questions about any of the presentations you've heard this evening. Ken, I think you're trying to speak, but you are on mute.
Okay, right. Now you can hear me?
Yes.
So what is the time frame in terms of the implementation of the soft, in soft robotics? It's not something that I certainly have read in general media. This is a new concept for me. I mean, how do you see that being implemented?
Yeah, so soft, I think the soft robots are getting much attention, like probably just from past few years. Just especially as I was saying, this we have these rigid robots which can do whatever we want in very precise manner. But when we want them to work in a completely unknown environments, we cannot program every specific detail in an uncertain environment. So that's where we want to bring the intelligence from nature, because natural systems, they can change, they can adapt very easily in an unstructured environment. So we're basically inspiring from that and designing soft robots, and especially for human robot interaction. We don't want to bring robots which are very hard in our homes, but we want them to be soft and helping us in different aspects of it. So the timeline is honestly, we still don't know how to control them. because they have infinite degrees of freedom. So that means like, for example, a human hand can be made very rigid robot with 2 links, and we can control exactly the position of that. But when it's made of completely soft systems, we still don't know how can we control the system. So I'm thinking probably down the lane, maybe in 5 to 10 years, we could actually see them coming slowly into market. As I said, they are already being used in food manufacturing, food handling, especially. There is a company called Soft Robotics Inc., which develops these grippers, which can be used in different food industry for handling the food equipment. But yeah, but slowly they will be coming into media attention more and more. Yeah, thanks for the question.
I have another question, if no one else does, on the agricultural issue. What's the progress been in terms of, I remember, I think it was a fellow named Despommier, Columbia, my alma mater, the vertical farm, indoor farming, because that enables much better control with a lot less pollution, so, and less use of water, less emissions. It's a controllable environment. How is that going along at this point? What do you know about that?
So I haven't looked at the updates in the last year, but from what I'm aware of, they're actually trying to make more use of vertical farms out in the Midwest. There are lots of questions about how to most effectively pick and plant from those fields, because they're trying to make these vertical farms as most compact as they possibly can. So, you know, essentially we're adapting an entire field of agriculture to a different space. And so that's kind of been the transition that people are trying to go through right now. But there are a couple startups who are working on expanding these. I know Australia is really trying to work on them because of their problem with forest fires. That's what I know of the issue.
So you think that'll be the future of farming to a much greater extent?
I don't know if I can answer that question. I think it is a good option. It's definitely, you may have noticed that there's a lot more hydroponic plants in your grocery stores. Yep. So I definitely think we are moving in that direction, but it's a complex landscape of how much the mass production farms want to shift over. That's a lot of startup cost for them. And, you know, whether or not people even like the taste of these hydroponic foods. If you've never tried one, I've tried side by side hydroponic versus normal lettuce, and they do in fact taste different, and they have even different textures. So it's a complex question.
Thank you.
Hi. I also have a question for Jessica, please. And thank you all for the fascinating presentations. Which areas are most susceptible to the red tide or to the kinds of algal blooms that you were describing?
So for specifically the red tide, we see that most commonly, at least in the United States, off the Pacific coast. It reaches from mid-California up to Alaska, and happens in kind of a cyclic cycle that every year based on the season, starting in spring, that is lengthening every year with warming temperatures and warming oceans. So usually it'll continue throughout summer and it'll start dying in the fall, but that's most of your harvest season for any sort of commercial fishing. It's also, you're seeing a lot of red tide off the coast of Europe, off of the UK and off of parts of India as well. There are, you know, I simplified it down to just the problems of dead zones and the toxic producing red tides, but there are many different species of these algae and even some bacteria that will sometimes get lumped into red tide that, you know, are happening everywhere. Like if you go to the Farmington, if you go to the Connecticut River, you can see both red tide algae and just normal toxic algae that form every year. And there's also cyanobacteria, which is a horrible smell, and it does not get cleaned out of our municipal waters very well at all.
And which areas are becoming more susceptible? Because you mentioned the impact on business, and I imagine that most businesses aren't thinking about this kind of environmental impact. Where should people be planning to have to deal with these kinds of problems in the future?
Where is most susceptible is definitely lakes. Any places where you have sitting water or low flux water, so water that's not moving they are the most susceptible. If you have low gradient streams, so in Connecticut, we have a lot of high gradient rivers because of all of the cliffs in Connecticut. But if you go to parts of the country that have less gradient, their rivers move a lot slower. And so they run into the same problem as lakes. They're much more likely to sustain these, the growth of algae because they're not being immediately shipped away by the flow of water. You also have a lot of estuaries like the Long Island Sound runs into this problem. They actually have a cyanobacterial bloom that's starting up right now. I saw it last night. So
Wow.
yeah, essentially slow moving areas.
Thank you. That's really helpful.
In the media, the red tide a year, 2, 5 years ago was almost always referred to as a mysterious red tide. I'm gathering from you that this is not mysterious anymore. We know what causes it. Am I right?
To the best of my understanding, like I said, there are multiple types of species going into this red tide, but yeah, most of them are coming from just an excess of nutrients, be they ammonia or also phosphate. Ammonia and phosphate are the two main makeup species of in our fertilizers. But yeah, in terms of the the biological processes that are going on within these bacteria and algae, that's not always fully understood. But a lot of times people are looking at ammonia from a fuel cell perspective and not thinking about the other side of, hey, we're making fuels, we're making excess fertilizer, this is great, but what happens afterwards? It's the constant human problem. Advance and then deal with the problems you created by advancing.
Thank you.
Yeah.
Are we going to do more of these sessions with, because these were great. You did one a few months ago. You folks bring things onto a level that makes it more understandable, and you bring some clarity. So I think it's great. I mean, these programs are really good.
I do encourage everyone to check newcanaanlibrary.org. We have our events calendar. I'm delighted to hear that feedback, so I really appreciate it. I do think these guys are wonderful, and you had me at Octopus. I love to read. It was fascinating. But we do slow down programming quite a bit. We just don't get as many numbers, especially with when it's nicer out and on Zoom. And we are hoping to bring back in-person programming. So our events calendar is a little lighter in July and August, and we're hoping to cut. Yeah, a lot of people just sort of leave town, and when it's beautiful out, we don't get very many people to log on virtually. So yeah, we have a long-standing relationship with Yale Science Communications. So
yeah, thank you folks for coming in and doing this. Thank you very much.
Yale
Lovely.
Science is great. Karen and I attend every meeting in person for years. Right now I'm in Nantucket, Massachusetts, and I wouldn't miss it. I enjoy it and I learn. And I think you're also unbiased and factual, and that's valuable today.
It certainly is. So much is propaganda out there. It's good to hear just straight science instead of a lot of opinion.
I agree.
Here, here.
Thank you very much to
Thank you.
our wonderful science scientists, panelists, and for the Yale Science Communications. Thank you very much for all of our participants and your patience with our tech issues this evening. Please do come check our calendar. We do have a lot of interesting things on the docket for the next few weeks, but we will bring these guys back, not to worry.
I love that you're volunteers. I love your enthusiasm, your smarts, and your sharing.
Yeah, thank you again. Have a
Okay.
good night and have a good
Everyone
summer.
have a wonderful evening. Take care.
Thank you. Bye-bye.
Thank you.